All right, welcome back. We are game 3001. That's Artificial Intelligence for Games at George Brown in the winter 2022 semester. And it's week 4, part 1 of our broadcast and recordings. And we're talking about combining steering behaviors today, flocking, what that is in more detail, as well as I'm going to be talking about assignment 2 details coming up. So let's get into that right now. So where we're sitting at week 4. So that's the week of January 31st. Today is the 1st of February. And again, we're going to be talking about dynamic steering behaviors in terms of combining them and those kind of things. We are also looking ahead. Next week, we're going to start pathfinding, which is a whole different way of doing things. So we're still going to move our autonomous agents, but we're going to move them more by them computing the best path or the shortest path to a location. All right, so that's what we're going to start doing starting next week. We're going to use a grid-based system. And then the following weeks, more things like points of visibility and more about line of sight. We're also going to be talking about A-star pathfinding in week 7, as well as different variants. Okay, so we're actually going to talk about A-star a couple of times. And again, by week 7, we'll have our assignment 3 released, and then we'll get into our mid-semester break, which is the week of February 28th. So after your assignment 2 is due, the week after that, you have an entire week break where you can kind of recuperate, generate, read. There might be some assignments that are outstanding for other classes that you're going to combine with other people to create, and that kind of stuff. So that's what's coming up in only a few short weeks. So just wanted to give you that on the horizon. Last week, what did we talk about? We introduced dynamic steering behaviors, and we talked about how it's different than kinematic in that we use velocity and acceleration, and mostly acceleration, what we found in lab to move our autonomous agent around. We implemented a couple of behaviors. We'll talk about those in a second. But we discussed in lecture, look where you're going, wander, path following, separation, collision avoidance, and obstacle avoidance. So if you haven't had a chance to take a look at that lecture, again, the lecture is recorded and has been posted up on Blackboard for you to look at. Even if you look through the information and if you're having trouble understanding, I think it's best to even look at it twice the speed or 1.5 times speed. You'll get some of it. You can always slow things down, slow me down, and have a chance to absorb things better. In our lab 2, which was worth 4% of your final grade, we learned more about the assignment framework, how to add game objects. That was over the last 2 weeks, so week 3 and 2, and how to do basic 2D collision detection. We talked about basic collision detection shapes and what is good enough. We discussed, how do we use the kinematic equation for movement, at least in my labs. We implemented the seek algorithm to some level of success, I would say, initially, and then we fixed it. We fixed any kind of problems, and the recordings show that we were able to do that. I ended up making 3 recordings last week, and for you guys to help you out with not just seek, but also look where you're going. You can always find the recordings that we have in class up on Blackboard. So here's Blackboard for this week. You can see that the current recording has a link up right here. So please make sure you take a look at it if you need to. As an example, if you miss class or something like that, that's why we do it. If you go to the content area and if you go to week 3, you'll see that last week we had 3 recordings. So all about dynamic steering behaviors in the lecture video plus 2 videos. So part 2 and part 3 were how to implement dynamic seek. We had some glitches. They were fixed in this one. So this took a little longer than normal. I recorded an extra hour and a half of stuff that I wanted you to make sure that you could get done so you can understand how this works. At least we don't know if I'm recording. Oh yeah, I'm recording. It looks like I'm recording fine on YouTube. So you should try it out. So the link for it should be, I'll share that link with you unless I made a mistake. The link should be right here. Let's take a look at that link. And if you wanted to, kind of look that up on YouTube, you can. So those are the 3. So again, we have our kind of the lecture video and 2 lab videos that I made last week. And also, Alex also records stuff on Blackboard Collaborate Ultra for those people who are using that. And you can always go to the recordings, right? For Alex, he also records all of his labs, and I highly recommend that if something doesn't work for me, then you can always check out what he's done, because again, we're sharing the course together. There's 2 instructors with potentially 2 different ways of doing things that can help. Sometimes looking at things from different perspectives is really great. So if you don't know where this is, it's up here. So take a look. So at least you have both recordings. You can see that the length here that he's done, and I've also done very similar things. All right, so that is where they are. I know some people have been asking, like, where's the recording for the lecture in the lab? Well, they're right here inside of content, and that's where it is. Shelly says, I was still having an issue where my ship was shaking a lot. I'm assuming I did something wrong. Yeah, so whenever you have shaking, that kind of stuff, or any kind of janky movement, and we'll talk about that a little bit. At the end of the day, it's what ends up happening is it's because you're trying to change the behavior or implement different behavior very, very quickly from frame to frame. And what we need to do is have a delay, implement a delay in terms of how it works. Okay, so that's how it ends up working out. Bhavya says, I had to rewatch both videos because the code from the recorded one looked way too different. Way too different. Are you talking about the recorded one in my labs or in Alex's? Bhavya? And I'll go back to Sam's comment. Yours. Okay. Yeah, I didn't change anything. All I did was modify what we started off with. Sam, all right. Also, I was trying to submit my lab 2 last night. For some reason, it is no longer there, so I can no longer submit the lab 2. Okay. It's because lab 2 is always due on Sunday, and there is no time frame where you can record, where you can submit late, Sam. It's either on Sunday or before Sunday. That's how it works. The one from our lab was so different. Yeah. Okay. Are you talking about from when you were in kind of the earlier lab, and then I did the later lab, and our later lab was different? I did modify stuff, Bhavya, because at the end of the day, the kinematic equation I was using was flawed, and I wanted to show you what that is. And we'll talk about that later on. I'll talk about the solution for what we did with the lab later on. Yeah, I'll talk about that, and I'll tell you how it works. So that's why I did that. And that's why I ran into some issues. Again, live coding. And that is unfortunate for sure. All right, so that's what that was. So again, lab 2 worth 4% of your final grade for the completed version. And so what are we doing this week? This week we're talking about combining steering behaviors and how that can work, flocking. We're also going to be talking about problems when steering behaviors are in conflict. How do you resolve those? If I have 2 steering behaviors that are combined to create an effect or a motion, a movement for the autonomous agent, and what happens when they're in conflict? How do we resolve those conflicts? Are there steps or possible solutions? Stuff that's due. Lab 3 individual is due Sunday at midnight. And here's the other one. Assignment 1, again, all around steering behaviors, which is a group assignment, is also due Sunday at midnight. Assignment 1 is due 10%. Okay, so please make sure that this is due. So this is value is 10%, right? And lab 3, that value is 4%. So this week is a 14% week. That's how it works, right? So assignment 2 has also been released. We're going to talk about that. 10% deduction every day when there is a chance to submit it late, right? That's for assignments. Again, it's up to Alex if he wants to extend you. I'll talk to him, and if we'll put out an announcement, say that it's open. But typically what we do is labs are shut exactly when they're supposed to be done. Remember that labs are supposed to be done in day. Even though we give you Sunday to complete it, that's your time frame. You're supposed to, complete it the day of the time we're together. So if your lab time with us is on Thursdays, the idea is that you're supposed to submit your labs by Thursdays, latest Sunday, to give you a time frame to complete it. So that is your time, right? To get things going. Assignment 1 is due on Sunday, I believe. Let me just check to see that that's true. And if it's not, I think it should be, because that's what we kind of said that it was. Make sure that that is true. It is due on Friday. Yeah, sorry. So that's due Friday. That's correct. Let's do this Friday. So let's just change this up. So this is assignment 2, Friday at midnight. That's why it's not a clash. And lab 3 is Sunday at midnight, which is 4%. All right. Says assignment is due Friday. Yes. Is there an assignment extension to Sunday? No. All right. Just wanted to clear that up. Thank you. All right. For that, that's cleared up. So it's Friday, not Sunday. Again, if things change, again, when Alex and I continue to have discussions, sometimes we move the assignment due date only because we want to try and understand how you guys understand. And if there's a great discrepancy in understanding, like if we think you should be at 1 point and you're not, then that's where we might extend you for a couple of days to give you some more time to complete it if there's a lot of details. But again, you've had 4 weeks to get this started, so it's not like it's a short time. It's not like we gave it to you 2 weeks ago and we said go, kind of thing. So I think it's pretty good. But let's move on. We'll talk about that again. Let's continue. So I wanted to talk about, before we get into the meat and bones of what we're talking about today, which is combining steering behaviors, I wanted to talk about assignment 2, right? Because it's on the horizon and I want to introduce it to you today. We'll talk about it again. It's not going to be the last time because I know whenever we introduce an assignment, then there's questions because you don't quite understand what you need until you start working on it. Then you have a bunch of questions, right? So here it is. Here is assignment. Here's assignment 2. It's due week 7. And this time we've made it Sunday because for this one, you need as much time as you can to get it done. Okay, so that's why it's Sunday, not Friday. This assignment's all around pathfinding. You may work alone or with a partner. However, I highly recommend you work with a partner on all of your assignments. And the reason for this is because there are a lot of details. You have other courses to do, not just this one. And I think working with a partner can improve understanding a lot and lighten the load, which is something that we don't want you to be overloaded with the stuff that you have to do. So mandatory criteria is marked, stuff that you need to do, and let's talk about our project setup. So again, you must use the template provided on Blackboard as a base, and that template is the assignment framework that we keep on sharing with you every single time. If the assignment framework has been updated, you need to use the most updated version of the assignment framework because it may include additional things that we've shared with you, okay? So always grab the latest version and start from scratch. You can always go back to the work that we do in the labs and copy paste some of the stuff that we have in there, but I recommend you start from scratch. It's a clean assignment. You know that there's no issues, no errors that are carried over from one lab to the other. Christian's asking, is its version 0.27? Yes, right now it's 0.27. That's the one. Okay, your assignment must include a start scene. So we know this. This is kind of like free 5 marks. You add labels for you and your student ID for you and your partner, and a start button. You can actually carry this over 5 free marks from the other assignment. Actually, if anything, like we said before, the assignment framework itself provides a button and some labels that you just need to make a little bit different, and you're good to go. So free marks, 5 free marks, 5% free for this assignment. So here's where all the fun happens, the play scene, where you'll be demonstrating pathfinding. You must include a tile class. So one thing we're going to be talking about with pathfinding is using some kind of division scheme. Okay, so a lot of times that, I thought all assignment 3 people. No, that's only for assignment 2. Assignment 2 is 2 people, not 3. Yeah. For assignment 2, 2 people, guys, from what I understand. Right? That's what we agreed on. So 2 people for assignment 2. So why did we do 3 people for assignment 1? Because it was your first foray into, kind of what you're doing. And what we want to try and do is give you a chance to slide into the programming a little bit easier. And so that way we wanted to really kind of reduce the load as much as possible for assignment 1. But assignment 2, you're going to have a partner. So you're going to do partner programming. And I think it's great because you get to understand a little bit more And by now you should have had some practice with programming and structures, the assignment framework, and so on. So it should be a little bit easier to understand. Assignment 1 is 3, yeah, because assignment 1 is easier. So what this does, this course ramps a little bit, right? So how do you figure out who to kick out? Sam, you don't kick out anybody. Give me a second and I'll explain everything, all right? So again, you must include a tile class because we're going to have a division scheme or something similar. You could include also, something that is your own version of the tile class and that can map its orthogonal neighbors. So we're only going to allow you to map, 4 neighbors, up, right, down, and left. We'll talk about pathfinding more again, what that means. And then you must create a grid of tiles. So every tile itself is a smart tile, and a grid of tiles allows you to create a division scheme for your game world in order for you to promote pathfinding for your autonomous agents. So again, you could use a vector in the standard template library or some kind of array structure of tile pointers. It's totally up to you how you want to do that data structure. Each tile object in your map should have a cost value associated with passing through it. So the way pathfinding works, and as a preview with this, is we kind of calculate the cost so far as we're moving from one position on the screen to the other. And then we try and calculate the shortest cost, the shortest path from one part of the map, normally the start tile, to the goal tile, which is at the other part of the map, okay? Ensure you select an appropriate actor sprite. Again, I recommend using the actor class. This could be a spaceship, a car, or an animated character, or other appropriate vehicle or avatar. This is up to you. So when we say, select a spaceship, please don't use the ones we've given you in class. Okay, and this, by the way, goes for assignment 1. If we've given you textures or sprites for assignment 1, please don't submit them back to us. This is for you to make your own. Right, or you can grab them from an open source graphics library, like, for example, OpenGameArt. That's perfectly fine, but don't use our own. Make it a little interesting. You are in a game program, and this will give you the opportunity to kind of customize your assignment and gamify it a little bit. The actor will be able to navigate the tiles by only moving right, left, up, or down to any open neighbor. So this is key because they won't allow, so what we're asking you to do is not allow diagonal movement, which is a little bit more difficult than doing it this way, okay? So, sorry, this is more difficult than allowing diagonal movement. All right, and the actor must be oriented properly using the look where you're going algorithm. So you're combining a little bit of steering behavior when it comes to moving, but not much, because really what you're doing is you're just reorienting depending on which tile you're going to, okay? So that's something you need to do. Create an interesting map. This is always a point of contention. What the heck is an interesting map? I've been asked before from one iteration of this assignment to the other. How do you make an interesting map? Well, you can do it several ways. You can have it so it's one big texture that kind of overlaps or overlays on top of the grid structure that's beneath it, that's invisible. Typically, that's what we do. You can also use a tile map if you want to. We don't have a tile loader available right now in our engine, but it doesn't mean that you can't figure out how to load tiles, as an example, into the engine. That's not impossible to do. Again, it's all depending on how much programming you want to do. And that it's overlaid on top of the tile and grid system. So again, this is for, visual aesthetics. And it doesn't mean that it doesn't have to be a tile map. You can make it just a texture or graphic that overlays. Again, you can make this creative if you want. Ensure the map includes obstacles, so mountains, walls, debris, whatever you're going to make it, that are impassable, so that you cannot pass through them and so on at all, or under them. You may use a tile map set or simply draw your map tiles individually. It's up to you. You can also just have your texture and the entire one big texture that kind of, represents different parts of your map. Add text label to the play scene to provide instructions for the user. Press F to find the shortest path or to reset the scene. Alternatively for this, you can always use I am GUI instead of the text to make this work. Add some kind of text label to the play scene to show the total path cost. Again, this can be done with I am GUI instead of you taking it up. I'm giving you these options to create a label if somehow I am GUI is difficult for you to use. All right, so although it's not explicitly stated here, I would accept you know, I am GUI instead of, when you're demonstrating, instead of labels on the actual game itself. Your play scene must include appropriate background music. Again, this is to gamify the experience. Ensure that the volume is set to a reasonable level. Don't blast the volume is what this means. And don't make it too low, otherwise it's useless. Add simple sound effects for various actions and or triggers in the play scene. So anything that you do, this may include but is not limited to the actor marching along the path, the actor finding the goal, etc. Okay, that's how it works. Requirements, you will create code to implement the A-star pathfinding algorithm in the start scene. Okay, so let's take a look. And we go through things like pathfinding heuristic and mapping function. That's worth 5 points. Use some kind of pathfinding heuristic of your choice. Manhattan distance or Euclidean distance are the recommended ones you want to use. We'll talk about what those two things are over the coming weeks to enable an A-star algorithm that you will create to calculate the tile cost from the goal tile outwards. This means that each tile will keep track of the cost so far based on the selected heuristic. So heuristic is an estimation. That's what this is, where you can use different kinds of algorithms. Manhattan distance, we'll talk about what that is, and Euclidean distance, which is the distance as the crow flies for the most part. Don't be scared because this is how it works, Aiden. A debug view. When the user presses the H key, your program will toggle into the debug view, which will display the tile borders. Okay, we can use, again, the util drawing functions that we have in our assignment framework to enable this functionality. The tile costs and the path information will also be shown in the debug view. Okay, so we can actually have that come up. Starting tile, when and only when the debug view is active, the user can left click on any open tile in the debug view and select it as a starting tile. Okay, how the heck would you do a left click on the screen when it's not a button? Lots of ways is the answer. One of them is to use a position. So you click somewhere on the screen and it returns the position of the tile. That is one way to do it. And this will become a unique feature of the debug state. So only when you're in debug state, you can left click on any open tile and the debug view, in the debug view, and select it as the starting tile. So that'll become the starting tile, okay? The goal tile, when and only when the debug view is active, the user can right click on any open tile in the debug view and select it as the goal tile. So what you can do is you can say, when the game starts, you left click and say that's the start, right click, that's the destination, and then this will become a unique feature of the debug state. When a new goal tile is selected, the mapping function will recalculate the distance from the goal tile based on the selected heuristic, Manhattan distance or Euclidean distance, which we'll talk about. Don't worry about the names. I know some people are like, what the heck is Manhattan distance? And we'll go through it. And note that the start and goal tiles cannot be the same. So you can't right click on the same location. You should have validation techniques built into your programming to disallow that to happen. Obstacle tiles. Your map must include obstacle tiles that are impassable. And this means that pathfinding algorithm will ignore them when calculating the shortest path. And the obstacle tiles should coincide with the interesting map as described in the setup. So in other words, if you're making something that's impassable and it's and you have a mountain tile, then that kind of makes sense, right? Because mountains should be perhaps impassable, or some kind of river tile, that you can't pass over, or something like that, or a chasm of some kind, like a crack in the earth that you can't jump over, or whatever. Then that is okay as well. It's up to you how you set this up. Okay. Sam says, so are you going to talk about how A1 is 3 people and A2 is 2 people? I just said that, Sam. I said A1 is 3 people to ease you into programming and to make it easier for you to understand the framework. And A2 is only 2 people because now you already know stuff, and that's actually the right size for doing these assignments. Let me tell you this, Sam. At earlier iterations of this course, A1 was individual. You did it on your own. And we found that it was a lot of work to start off because you're learning many things at the same time. It's not meant for you to sink or swim, actually. No, what it's meant is for you to be, you have to be, in order for you to become good at programming, especially for AI, you need to do it regularly. Sam says, so should we be making entirely new groups from A1 groups? Yes. And I'll show you what they are. They're actually A2 groups, which we'll talk about in a second. All right, finding and display the shortest path. Again, please hold your questions until the end so I can go through this, and then I probably might answer most of your questions before you answer them. And if I don't, then we can go with questions, and then we can go through this thing. So again, finding and displaying the shortest path. This is mandatory, and it's worth 20 points, so 20% of your grade for this assignment. When the user presses the F key, or your program, or some other key that's in IMGUI, your program will calculate and display all viable paths to the goal tile and will highlight the shortest path. Highlight the shortest path. You can make it so that the tiles light up. You can make it so that there is, arrows that tell you where to go. Lots of ways to do this. And you also need to move the actor along the shortest path. So that's mandatory. When the user presses the M key, the actor will march along the shortest path until it reaches the goal tile. One of the challenges to try and get the actor to march along is to slow the actor down. So movement should be fairly slow so it doesn't instantly teleport from the start to the goal, because that can happen because it's so fast. If you let it, that it'll move right there. So you need to limit the space it goes. It's almost like doing a seek algorithm from one tile to the other tile. And, when you get there, pause for X number of frames before you go to the next tile. That's how it would normally work. That's how marching across. I would like you to think about this as almost like when you play a board game like Monopoly and you count the squares on the board, 1, 2, 3, 4, like that. That's how your actor should march along the board. Okay. Notice that the finding shortest path calculation and the moving the actor across the shortest path are two different functions. Okay. Use Git and GitHub for source control. You've been learning how to do this throughout the time we're together with labs. And what you want to do, of course, is remove garbage files to have a clean submission. All right, that's important to do. Short video to demonstrate, your application, your assignment, and tell us how it's done. Please don't read line by line, as that doesn't do anything for us. Show us that everything is working the way it's supposed to, and highlight those areas. Again, this assignment will also be accompanied by a lab report, and I will also give you the lab report for assignment 1 on Thursday. So you'll have it ready for yourself on Thursday that you can attach. Almost like a checklist that we do for our labs, you'll have a lab report for your assignment in order for you to make sure that you get all the requirements done. Again, I will share that with you, and so will Alex on Thursday morning. Okay, so this was coming up, and this one there'll be a new one for you for this one as we approach assignment 2's due date. Okay, again, 10% of penalty for per day late for assignments, and again, instructor provided code is allowed. We always try and help you out with the labs. However, using external code could result in a mark of 0 for the entire assignment. Make sure you check with your instructor, myself and or Alex, as an example, if you have a doubt around this. In other words, if you're using a large patch of code from somebody else, why? You should be doing it on your own. And email if you're not certain. Send us an email, copy Alex on it, and say, hey, I'm thinking about using this code that I found in this place. Is that okay? Chances are we're going to say, no, it's not okay, unless you have a really good reason or some special effect you want to use that we didn't cover in class. All right, so use your own code provided on the PowerPoint slides, as well as stuff we show you in labs, is the primary way we want you to do assignments in this course. Assignment weight is 15% of the course grade, so although you only have 2 people working on it, it's worth 5% more than assignment 1. Okay, just letting you know. And then here's the brief breakdown of everything. Again, we'll show this, these same things in your lab report for the most part. Questions around assignment 2, anything that I've covered here in terms of what we're looking for and from assignment 2. Again, you may not have the right questions right now because, like I said earlier, you don't know anything about pathfinding for the most part, so you may not be able to ask the right kinds of questions, and that's okay. But please read through the assignment details. Assignment says, is it moving while holding M or M key, press, and it automatically moves until it's there? So you press the F key or some other key as an example, and you find the path, and then you press the M key once, Simon, and it automatically moves step by step, clunk, 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 just like that, from one tile to the other tile until it gets to the goal. Right. 20th February is a Monday. That's it. Oh, that's incorrect. Okay, we'll adjust that. It should be the 27th. That's weird that we miscalculated that. I'll update the details for the assignment. Yep. Thank you for that, Anson. Awesome. All right, so let's talk about how to do the assignments. Remember that in the assignments, whenever you submit something, there is a set of groups. So for now, what we've done is you have A1 groups as an example. Let's go back to the beginning. You are assigned an A1 group set right now, right? And again, it's from 1 to 3 people. And A2, if you notice, for you to do A2, you can't use A1 groups. You need to resubscribe to a new group set that is only 2 people. All right, so that's why you need to redo that. There is no who are we going to kick out? You don't kick out anybody. You reform into new A2 groups that are, there's 40 teams, that have been submitted on Blackboard, and you and one other person, again, would join these groups. Okay. What Hanson says is correct. It's still going to be due Sunday. Okay. So yeah, thank you, Hanson, for that clarification. So we can adjust that again. And if I'm not wrong, just to make sure that that is not incorrect, because it says Sunday, February the 28th, I'll just adjust that right now. Because it needs to be on Sunday, not on Monday, guys, because Monday will be part of your vacation. You don't want me to spoil your vacation with or vacation time off, I would say, with a assignment to be done on the Monday. That'd be terrible. It means you're going to be losing one of your days, and that'd be bad. You have other things that are due. Adjust it. Thank you. Okay, so any questions around assignment 2 beyond that stuff? About groups. Yeah, Aiden, talk to me. What about groups? This is the time to ask. I'm moving on to the actual stuff now. You cannot stay in the same group. So again, if you look at the groups online, under users and groups, you'll see that there are A2 groups now. A2 groups, which is another set of groups, have been created for assignment 2, right? So only A2 groups can submit. If you try even see your assignment 2, you'll see that you won't be able to join or submit assignment 2 or even open assignment 2 until you join a group, all right? That's in A2 groups, right? That's a requirement. So please do that as soon as possible. Okay. So Simon says the map textures don't need to be squares, do they? Just the pathfinding invisible tiles. Yes, the pathfinding invisible tiles will be it could be squares or rectangles. We'll talk about how to do that. But the front, you could use tiles, or you could just use an interesting map that is one-to-one with the kind of tiles that you show in the that you have in the background. So, for example, if I have some impassable tiles that you mapped below the texture, as long as the texture on top is contextual. So if you have some kind of impassable tile, then there should be some kind of impassable texture on the top of it. That's all I mean. Are we forming them now, or would it be open after the assignment 1 submission? It's open now until just before the submission, just before week 7. After week 7, they're still open, but you won't be able to submit. Why are you reducing the group size? Miguel, I talked about that already. The first group size, assignment 1, was 3 people to ease you into programming and to get the requirements right, reduce some of your load. You didn't know the assignment framework at all. Now you know it a little bit, and it'll give you an opportunity, to learn stuff. That was assignment 1. It's only worth 10%, so it's not as critical. Now, when we get into assignment 2, you'll be reduced down to 2 people, as an example. And when you do the assignment with 2 people, it'll give you more responsibility, but then you know the assignment better, the assignment framework better. And again, it'll make it so that it is the right level of challenge. Simon says, so do we need to join an A2 group to view the document, or is it open? You can see the A2 document. I've made it separate as well. So one thing I've done is even if you don't join, if you go to assignments, you'll see that there is assignment 2 details. You can see the document right here. The date is wrong, but I'll update that date correctly. It'll be Sunday, February the 27th. Is assignment 1 being easier the same reason why the due date is Friday instead of Sunday like everything else? Correct. And also because you have your lab that's going to coincide with it. Yeah. Yes, Thomas. Assignment 1 is easier. No problem. Okay, let's move on. I'll take other questions about assignments later on. But again, I want you guys to understand a couple things, if possible. And please don't take it the wrong way. We're not trying to make this oppressive. It's not supposed to be oppressive. What we're trying to do is we're trying to set the evaluation so it's the right level of challenge for everybody. And it also evaluates your understanding of AI. That's what it's for. It's not meant to punish you in any way. So if you think you're being punished by going from 3 people down to 2 people, that's not the intent. And if anything, it's supposed to give you more responsibility because it's only you and your partner to get it done, right? And so that way you can learn more. The more you do, the more you learn. Okay, so that's what it's supposed to be for. Again, not to punish you, but actually to make it more fun, if anything, and to give you a chance to really get your hands into AI. All right. Again, an iteration of this course previous to this, every assignment was individual. You did everything on your own. Okay, let's move on. So far what we've talked about is kinematic steering behaviors and dynamic steering behaviors. This is the lecture portion, guys. And what I wanted to talk about today a little bit was something called combining steering behaviors, okay, and flocking a little bit as well. So a lot of times just by themselves, steering behaviors, if you do one after the other, you can achieve a pretty good degree of success when it comes to movement for your AI. But in many games, again, we only have like just a given location. We have some kind of seek, but sometimes what ends up happening is we have some more complex needs for an autonomous character. An example would be for your assignment 1, obstacle avoidance. You're seeking the target. That's what we've asked you to do, right, for assignment 1. So let's visualize a little bit what we're asking you to do for assignment 1. And not the finite state machine. We don't need you to do that. Let me just kill this one. But let's talk about assignment 1 a little bit in terms of just some visualization. So the obstacle avoidance part is, let's suppose I have an obstacle, right? So here's your obstacle, and it can be set up like this, or you could even alternatively set it up this way. It doesn't really matter which way you set it up. You have your goal. Okay, so there's your goal, let's say over here, right? And you have your autonomous agent over here. As an example, let's make it so that it's a bit of a rectangle with maybe some additional shape characteristics that gives you a orientation of some kind. Okay, so that's kind of how it looks. There's your autonomous agent. So you have the agent. That's what we've asked you to do. And we've asked you to also have a target. So there's the target. I'm going really slow right now just to get you guys into thinking about this again for assignment 1. And then you also have the obstacle. Okay. So your job is to position your agent so that the obstacle is in front of it for one part of the assignment. And what you want to do is navigate around the obstacle and get to the target. So really you have 2 goals. So let's talk about the goals for this one. So goal number 1 would be seek the target, right? And goal number 2 is avoid the obstacle. You can actually interchange these goals. It could be avoid the obstacle and then seek the target. But really, it's the other way around. You can say the first goal is really to seek the target. So you can draw a straight line, and we can do this from the agent to the target, right? And if you did this, you'd pass through an obstacle in real life. You would collide and the agent would explode or something bad would happen. So you don't want this to happen, right? What we're going to look for, we're going to be talking about today with combining steering behaviors, is how do I create a intermediate goal or a sub goal where I have some kind of radius. You can use a radius of some kind around the object. Let's use a different color for the radius. So let's use an orange color for the radius, right? And do that again. So let's suppose you have some kind of intermittent goal, and the goal might be something like, let's put that goal as black again. Let's say, for example, you have an intermittent goal that is here, and this goal here, and let's call this the sub goal, is somewhere where you want to go first. You want to kind of go to that place first, as an example, before you go to the target. So this is a way of combining steering behaviors. You can also use some of the methods we talked about last week, which were things like line of sight. So let's draw a line of sight line. Line of sight. Let's draw a line for that. And we talked about many ways you can do that. You can have feelers or whiskers. You can also go, some people were talking about using kind of line of sight lines that look like this from last week, where you can move your autonomous agent towards the obstacle, right? Let's just do that. And what you can do with the obstacle is, as you move towards the obstacle, as an example, you can move straight on, then you decide which way to turn. Let's suppose you turn this way or this way. You turn a little bit at a time, so you don't turn right away. You don't do this right away when you hit that location, but rather what you do is you turn a little bit and then you move forward. You might slow down a little bit. That's something that we talked about, right? And what you're doing is slowly you're moving towards the obstacle to avoid collision. Now look at this. You can get into a situation where you might even collide in your attempts to avoid, right? Really depends on your movement and the way it works. So these are the kind of things that you want to try and think about. How do I move there? The alternative is to have some kind of sub goal. And the sub goal might be something where you have multiple, like I talked about before, multiple nodes, if you will. So there might be a node over here that's outside of the range. Let's make that black. That's outside of the collision range. So it's kind of like some place where you can go and you can seek to that sub goal, as an example, without kind of using feelers at all, right? To do that. So instead of using feelers, you would have a central line of sight. And if your line of sight is obscured, so again, what you could have is a line of sight. Let's make that line of sight a different color, like blue, right? And let's suppose I have a line of sight. You draw a line of sight from your agent to your target. This is an alternative way of doing it. And that line of sight shows that there's an obstacle in the middle, because what you can do is you can do line-line collision detection. So example would be, that this line, as an example, collides here with the obstacle. So you have something that goes between you and the target. There's a collision between you and the target. So therefore you don't have line of sight. And if once you don't have line of sight, then you can readjust your seek. So you're doing seek to the target, but what you do is an intermediate seek from your agent, to the sub goal, and then from the sub goal to the target. That's something that you can do instead, all right, as an alternative. So these are different methods that we talked about on how to avoid, colliding with an obstacle. Remember that obstacle avoidance is with an obstacle or an object that is stationary, a wall or other obstacle. And collision avoidance is with two autonomous agents that are moving, okay, typically. Christian says, so we have to calculate where the sub goal is. Well, or yes, you could do that. Or you could have the obstacle tell the agent what the sub goals are. In other words, the obstacle knows the locations of the safe places to pass for the agent and informs the agent, kind of like cheating, actually, right? But it's not a terrible way of doing things. The challenge is when I have more than one of these in my scene. So if I have multiple obstacles, one after the other, and the target is obscured behind many of them, we're going to see that is going to be a challenge. And the reason why this is a challenge is because the AI we're talking about in this course so far is very sparse environment, an outdoor environment that has very few obstacles and not occluded with a lot of them. The more you add obstacles to your environment, the more challenging and janky the motion of the AI is going to be when you use basic steering behaviors, because of the conflicts that can occur. You're giving the steering behavior a couple of things to do. A, avoid walls. B, you might have some kind of seek. Which one is taking precedent? Is seek weighted more heavily than avoid, or is avoid weighted more heavily than seek? Right? Obviously, in my mind, it should be the latter. Right? So it should be something that is like this, that this is more important in many ways than seeking. Make sure you don't hit anything while you're going to the target. Should be something that you think about for your agents. And this is kind of implicit. It's not something that we've told you. We didn't say you must avoid all obstacles, as an example. We say that this is an obstacle avoidance example, but the goal is to actually get to the target, right? So that's kind of the goal, right? So that can be confusing. So going back to that, there might be some kind of conflicts that we're going to be talking about as well. So again, moving an autonomous agent usually needs more than one steering behavior, right? And it needs to reach a goal, avoid collisions like we just talked about with other autonomous characters or walls or whatever. And we want to think about it as if it tends towards safety as it moves, generally is what we want to do. Otherwise, it doesn't make sense. Then it's not really intelligent in any way. If we're creating an intelligent agent, we want it to act somewhat intelligently, right? So again, wall and obstacle avoidance can be particularly difficult to get right, especially when we have multiple behaviors at play and a constrained environment, which we're going to talk about soon. In addition to this, when it comes to steering, there might be more complex steering when we have flocks of autonomous agents or formation that we have to adhere to. Aiden says, just walks through walls running at you. Yeah, no, we don't want to run through walls in any way. That doesn't look good. So what we want to talk about first is this idea of blending and arbitration. And there's two different things we're going to be talking about here. So combining steering behaviors, again, it creates complex movements. And there are two methods of combining steering behaviors we can use, usually either blending and or arbitration. Let's talk about blending first. So what the hell is blending? So each method, it takes all the steering behaviors in place, but what is blending? Blending uses weights and priorities, right? And what happens is it's pretty good when we use weights and priorities. So which one do we want to do first? Avoid walls or seek the target? That's what we talk about here. But somehow it can be foiled. We're going to talk about how it gets foiled when there's lots of constraints in the environment. When I mean like lots of obstacles or other agents or a very busy environment, it can be foiled. Arbitration, on the other hand, selects one or more steering behaviors to have complete control over the autonomous character. And the way to do the arbitration scheme is it kind of sits there and says, what's my, how do I arbitrate or manage between one kind of steering behavior and another? Very kind of a same approach as blending, but it kind of makes a decision. So the simplest way to combine steering behaviors is to do weighted blending. Okay, that's kind of the simplest way to do it. Let's think about the problem. Okay, so here's the problem, guys. Suppose we have a crowd of rioting autonomous characters in our game, and the characters need to move as a mass while making sure that they aren't consistently bumping into each other, right? So let's think about games like that. What games could be like that? Racing games is an example, right? Some kind of crowd of rioting autonomous characters that are moving in the same direction, as an example. Each autonomous character needs to stay by the others, so there's a little bit of cohesion. Maybe you could have a bunch of zombies or some kind of, maybe soldiers is another scenario, while keeping a safe distance, separation, so that they don't overlap, right? This also could work in a space game where you have space enemies. You don't want them to overlap. They're kind of moving in a flocking pattern, as an example, but they don't want to collide with each other and destroy each other. That doesn't make any sense. They want to, err on the side of safety, safe movement, as opposed to movement that's going to be bad for them. So let's continue with the problem. Their overall behavior then is a blend of two behaviors, really. If you think about this, arrival, I want to get someplace safely, at the center of mass of the group, and separation from nearby characters, autonomous characters, right? So at no point is the autonomous character, doing just one thing. It's always taking both concerns into consideration, both things at the same time. I'm thinking about some kind of arrival and some kind of separation. And sometimes what this means is we want to use a steering behavior called cohesion, so staying closer together, and separation, which means making sure that you're some distance apart from the other autonomous characters. So again, here's a possible solution. A group of steering behaviors can be blended to act as a single behavior. Each steering behavior in the portfolio is asked for its acceleration request, and these accelerations are combined using a weighted linear sum, so some kind of way of combining things. And then the final acceleration from the sum may be too great for the capabilities of the autonomous character. And so what we do is we trim the acceleration or the velocity, clamping it into a maximum speed, so that way we don't go crazy. We don't make the autonomous character accelerate to infinity, which can happen if you're not careful. So the original research into these steering behaviors was by this guy, Craig Reynolds, and he modeled movement patterns of flocks of simulated birds known as boids. Okay, so this is kind of a common thing when it comes to AI. And normally they're not implemented in a game. Flocking is the most cited steering behavior, and sometimes people, kind of interchange the two. They might say something like, flocking and steering behavior is the same thing. No, flocking is a result of combined steering behaviors, combining steering behaviors to create a flock-like effect or simulate a very organic motion between different autonomous agents. That's what it's for, right? So again, the flocking algorithm relies on blending three simple steering behaviors. So you want to move away from boids being the simulated autonomous agents, right, that are too close, that's separation, right? Move in the same direction at the same velocity as the flock, alignment and velocity matching. You want to move in the same velocity, and move toward the center of mass of the flock, cohesion. All right, so that's something that we want to be able to do all the time. So a lot of steering behaviors happening all at the same time. This is a great example of combining steering behaviors to have an effect, right? So again, what is cohesion? It calculates its target by working out the center of mass. So example, this would be the center of mass, right, of the entire flock. So almost like an average position could be a way of doing that. It then hands off the target to a regular arrive behavior. So I want to arrive at the center of mass, right? And using equal weights is okay. Now, what happens when we arrive there? Well, we keep going, right? We go to the next position as we're moving, as an example, and we use average velocity and velocity matching, and that center of mass, if you will, keeps moving. It's a moving target, so it's not something that is, something that is static. It's a moving target for all of the boids, and each boid, each autonomous agent has the same. Uses the same kinds of steering behaviors. So each one of them looks out that they're not too close to the other one, but they're not too far from the center of mass, and that they're pointed roughly in the same direction and moving at the same speed. Those are all different things that are happening all at the same time. Very interesting. Again, to get more biologically believable behavior, or genetic behavior, if you will, separation is more important than cohesion, which is more important than alignment. So it's more important to keep separate. And then the second priority is cohesion, keeping closer together, so not too far apart, right? And it's more important than alignment. So even if I'm not looking in the exact direction all the time, it's more important to keep separate, but not too far before you actually align properly. And that's where you can have some orientation differences, as we saw earlier on, where some of them are moving in different directions. And you can see that some parts in a nice algorithm, some parts of the flock, separate from the flock and join other parts of the flock, right? Which is kind of interesting as well. Okay. So again, in most implementations of the flocking behavior, it is modified to ignore things like distant boids. All we want is a very short-sighted kind of view of what's around us. So again, each behavior, there is a neighborhood in which other boids are considered. So things like separation only avoids nearby boids, but not all of them, right? So if something is really, really far away, we don't really care about that one. And why do we want this? Because otherwise it's too computationally expensive to think about the entire flock as opposed to the nearest boids, right? So you have some kind of range, if you will. And cohesion and alignment calculate and seek the position, facing, and velocity of only neighboring boids. So we only care about those things, as opposed to boids that are far away. Again, the neighborhood is mostly commonly a simple radius, so what's around my autonomous character, although the guy who created the flocking behavior, he suggests it should have an angular cutoff. So for example, here's the radius, but we only care about what's directly in front of us. We really don't care about what's behind us too much because, again, some kind of cone of visibility makes more sense than understanding everything in the radius because, again, you have too many calculations. Okay, that's how, we're trying to optimize the algorithm as much as possible when we're talking about this. So there's some problems when it comes to blending, and a lot of times blending is used, like I said earlier, in very sparse outdoor environments, okay, rather than indoor or urban type environments. And the reason for that is because it becomes very challenging because one priority conflicts with another one. Okay, this idea of conflicting priorities. Again, in more realistic settings, autonomous characters can often get stuck. You'll see them getting stuck, even in the best games. They'll get stuck in a wall, or they'll get stuck facing the wrong direction. Even some AAA games have that problem, right? Because they're trying to, kind of decide which make the right decision based on what they're supposed to be doing, right? But some of these problems can be mitigated. We can fix them through introducing arbitration into the steering system. So again, we're combining or blending behaviors, but now we're also going to be talking about how to arbitrate the challenges. Let's talk about something called stable equilibria. Guys, again, don't worry about the terminology. The idea is what we want you to get. So stable equilibria. So blending steering behaviors, right, cause these problems or some kind of conflict. And it can lead to autonomous characters doing nothing, being trapped in some kind of equilibrium state where they don't move one way and they don't move the other way. So here's a character as an example that's trying to reach his destination. Here's the target, but meanwhile, while avoiding the enemy. Okay, so let's think about the behaviors that it's trying to do here all at the same time. It's trying to use the avoid or algorithm. I want to evade or flee from the enemy. That's the enemy. But at the same time, I have a goal to seek the target. Which one do I do first? Avoiding or seeking? That's a challenge, right? Again, you might think that, and I would think the same thing, that you should probably make your characters, depending on the type of game you're making. Again, this is very situational, right? Because if you're making a zombie game, who cares if there's an enemy in front of you? You want to seek the target, right? If you're making a game where the autonomous characters care about themselves, like guards, maybe you want to avoid the enemy first. It really depends on the type of game that you want to make. But either way, this can still cause an equilibrium situation. And we don't want an equilibrium, okay, as much as possible. Okay, so an equilibrium means that, neither one nor the other takes precedent, especially if it's in a special spot where it's the right place to flee, but at the same time, it's the right place to seek the target. So again, when we think about this, the seek steering behavior is precisely balanced against the evade behavior. And as long as the enemy is stationary, numerical instability, which is like floating point errors, will give the character a minute a minute lateral velocity. I might have some kind of velocity where I go up or down. That's what it means. And slowly, it's going to skirt around increasingly quickly before making a dash for the destination. And this idea, because of this numerical instability, floating point errors, is called an unstable equilibrium, where the character can escape somehow, right? Because, yeah, we're in a bad state. We're kind of in a state where we don't know what to do. One priority is conflicting with another one, but we can figure the character will work it out, over time, based on the numbers that you put in. By the way, when we say work it out, we're hoping that the character is going to work it out. Here's another situation where the character can't work it out. Let me explain this. Now, instead of having one enemy, we have a target to seek. So we have a couple of priorities here. I want to seek the target, but I have two enemies to avoid. Okay, so now what do? Do I ignore the enemies and keep going to the target? A zombie situation. Who cares if the enemies are going to kill me because I'm mindless? Or do I try to avoid the enemies, 1 and 2, but because of this area, which we like to call the basin of attraction, right? Then what ends up happening is that this creates a stable equilibrium, which means that once we create an equilibrium that is stable, the character will literally not move. It will just stay there because it doesn't know what to do, right? We want to seek, but we want to both avoid, and it's not going to do anything because if the seek and the avoid is the same strength, It's literally going to sit there. That's what's going to happen because it has no place to go. It can't go lateral this way or lateral this way because either way it needs to avoid, but at the same time, we have a strong seek requirement. So there's no escape for the character, and this is a bad situation. So this is way worse than this. This is I can escape this way or this way. There's ways of avoiding the enemy. Here, there's no escape. If I go up, I'm still going to get trapped. If I go down, I'm still going to get trapped. So I'm not going to move up or down. The only thing is to move this way, but because I have a seek target that is also part of my priorities, one thing cancels the other thing out. And a lot of times, guys, you trying to debug the situation is really challenging in AI. Really super challenging. So again, this idea of a basin of attraction, which is a large, which is a kind of a region in the level where an autonomous character will fall into the point of equilibrium. So basically, it's like I can't go this way and I can't go that way because my priorities are conflicting to the point where my movement rate is 0. I'm going to stop because if I move in any direction, either I'm going to get hit by an enemy or, or I don't know, hit another, it could be I'm going to hit another friendly character. You never know, right? And we don't want that because a lot of times AI is trying to find a safe path to the target, typically. Again, if the basin is very large, then the chance of an autonomous character being trapped are also very large. And when we think about unstable equilibria, which is what we want, right? So if you get into a situation where you want to arbitrate one way or the other, we want to make it as much unstable as possible, a way of getting out. But really the basin size of perfectly unstable equilibria would have a basin size of 0, which means there wouldn't be this situation where you have this big basin size. Think about this as a big bucket that your character is moving into. Uh-oh, what am I going to do? These guys, if they're moving at the same time, I'm in deep trouble. The only thing I can do is move this way, right? So again, it could be also basins of attraction. It's not just about locations. It could be orientation as well. So the other thing we have to think about when it comes to problems is this idea of constrained environments, right? So constrained environments in 3D, not a lot because I can move in X, Y, and Z directions. So I can imagine I'm in space. If I'm in space and I'm playing a space combat game, like for example, I don't know, X-Wing, some kind of X-Wing game, Starfighter or something like that, then what's going to end up happening is you still have the ability for you to turn your ship or your craft to different directions. Same thing for autonomous enemies. They can kind of find some kind of trajectory, a safe trajectory for their motion because we have multiple dimensions to move in, not just 2, right? 3 dimensions. And many games, however, like yours, the ones you're doing for assignment 1 and 2, are constrained into 2D worlds. A lot of times they have indoor environments, right? For example, I'm inside of a building. I'm on a racetrack, or there's some kind of flock or formation. Like, for example, I've got a formation of enemy units, let's say guards that work together to defeat the player, but they're in a formation and they got to pass through a corridor. How do I do that? Right? That is very complex, right? And it can mess up some of the requirements, some of the priorities that you have for your autonomous agents. So here's an example of some constrained environment. I have a priority to pursue the enemy, right? I have a priority to avoid the wall because I don't want to crash into the wall or I'll get hurt. So what do I do? Because I have a direction of where I'm going to go with pursue. Remember, pursue, what it does is it's different than seek in that I calculate where the enemy is going to be. So imagine I'm defeating myself because I'm saying, okay, the enemy's probably going to be over here somewhere. That's where he's going to be, right? So that's good. But at the same time, I want to avoid the wall. So try and go this way. And then the result is going to be some vector this way, which is on the other side of the wall from the enemy, which means I'm not going to ever get to the enemy. This is a problem. It's a big problem, right? Because at the end of the day, it's going one, kind of priority conflicts with the other ones. So, so again, it doesn't make it really nice when it comes to a constrained environment like being inside, okay? The other problem that's really bad is when I want to pass through a tunnel or between 2 obstacles. This is another case, edge case, that we have. where I'm using ray casting to avoid, to do obstacle avoidance, right? Like a wall avoidance or whatever, but meanwhile, I have a target that's over here out, at the other side of the wall. I want to be able to navigate somehow to the target, but I can't because of my speed and because of my direction. I'm looking where I'm going, and chances are my route for the character is going to be over here, which means I'm going to miss the target. That's also a problem. And why? Because we see this a lot because we want to try and go through a narrow doorway or some kind of tunnel, and that's really challenging. And obstacle avoidance really kicks in, and it sends our autonomous character past the door because it's just too close or whatever, especially depending on the speed that we're moving in. And again, this takes a lot of debugging. How do I deal with a doorway? And there's some techniques that we can use. For example, we can have some sub goals, like we're going to talk about later, where we can kind of navigate through the doorway in a different way. We can also combine, which we're going to talk about soon as well, our regular steering behaviors with pathfinding, which is what we're going to learn starting next week. One biggest problem that we have for autonomous agents is the idea of nearsightedness, right? We can't really see everything in the distance. The detection radius is interesting. I can have some detection radius where I can hear stuff. But imagine that I can only see or hear within my neighborhood. The same thing that keeps flocks working properly are the same things that really makes an autonomous character in a constrained environment or an urban neighborhood or something like that really bad, right? Because at the end of the day, as human beings, right, we don't just act locally like autonomous agents do. They use steering behaviors that act locally. Human beings kind of take everything into account. We look around and we go, okay, I'm in a dark alleyway. I got to make sure that I get through here. How am I going to get through the dark alleyway? I'm probably going to be in the middle of the alley or at one side or the other, right? Because depending on what my goals are, right? But an autonomous agent might go, tight alley, avoid, and like move out of there already, and maybe have a longer path to get there, right? So that a lot of times what they'll do is steering behaviors by themselves or even combined because of conflicting priorities will take the wrong course of action. All right, that's not what we want them to do. Okay, so here's another example of a figure, right, trying to do wall avoidance, but also chasing another character, right? So, I mean, again, depending on my ray, when the ray hits, especially if I have a ray that's a single ray, as an example, which way do I avoid this wall? I could go this way, or I can go this way, right? And by this just depends on where the ray hits the wall, on this side or the other side. Let's say over here, I might decide to turn this way, and because I'm short-sighted, I don't know that this is a dead end, which means, guess what? My autonomous character, this other character, is going to get away, all right? And it's not going to take the right route. A lot of times it won't. And we're going to see that even with pathfinding. It'll take the wrong way, depending on the algorithm. So there's really no way to augment the steering behaviors to get around this. Not really. Not a great way of doing it. Again, any behavior that does not look ahead, I don't have a look ahead, or I don't have a very large line of sight. I can't detect where I see walls coming up, as an example, will be foiled by stuff that's on the horizon, that's coming up. I haven't seen it. Remember, the character only has limited amount of vision, right? So Christian says, well, rays aren't very good. Well, they are in a non-constrained environment, right? But they're not that great in an urban environment or a constrained environment or an indoor environment or a racetrack environment or an environment where I have lots of flocking or, some kind of enemies that are in, or characters that are in a formation. In those cases, they're bad, right? Because they can actually lead us to a bad thing. Pathfinding is another way of doing it, combining pathfinding with some kind of line of sight, where we know the shortest distance to the character. Obviously, in this scenario, this distance here is just as, if I go this way or if I go this way, it could be equidistant depending on how I'm doing things, right? Example, if I match the distance, the actual line, if I kind of map a line, and this is, let's say, Euclidean distance as the crow flies, you're going to hear about this next week, right? Euclidean distance, the distance between, my character as the crow flies to my target, whatever that is, right? If I go this way or if I go this way, the distance might be the same. But what we get here, as an example, is we might be able to detect this wall over here. And we can change the pathfinding algorithm to basically block out this area, saying that this area here is not viable. That's what the pathfinding algorithm will do for us, right? Again, within reason, because pathfinding, the problem with pathfinding also is it takes computations, right? So if I do really deep, many kind of levels deep in terms of how far you want to take it, then it might take a long time for you to figure out which way to go. Meanwhile, the characters keep moving right away from you. So pathfinding can definitely help. Really depends on how you implement your pathfinding algorithm. So we're going to talk about that as well. And sometimes pathfinding can actually work against steering behaviors as well. So let's talk about something called cooperative arbitration. All right. So now we've been talking about algorithms, steering behaviors that only care about themselves. They don't care about what other steering behaviors want you to do. You might have two conflicting steering behaviors, and who cares? One thing wants you to do one thing. We weight them with another thing, and most likely it's going to be okay. But in constrained environments, and cause problems. But what about cooperative arbitration, where you want to calculate the result, right? When we want to cooperate together to get the right outcome, the right result, right? Again, when we blend, advantages are individual steering behaviors are very simple and easily replaced. We can switch one for another. I can prioritize which one I want to do next. And I can also test them on their own. That's the advantages. But we just talked about a significant number of weaknesses based on the environment, whatever that is. So a possible solution is this idea of cooperation. So here's an example. An autonomous character is chasing a target using a pursue behavior. Remember, pursue is calculating where it's going to be. At the same time, it is avoiding collisions with walls, wall avoidance. Okay? So here's the problem. The collision is imminent, so it needs to be avoided. Okay? The collision avoidance behavior generates an avoidance acceleration away from the wall, right? And because the collision is imminent, it takes precedence, and the character is accelerated away instead of following the target. Okay, so this is what can happen. So what's a possible solution? Well, we could blend, right, the pursue and the wall avoidance behaviors, as we saw before, and we might, depending on the floating point errors, when it comes to calculations, we might be able to get into an unstable Equilibria position, as an example. But even in this case, it would still be noticeable because the forward acceleration generated by pursue is diluted, and when we say diluted by wall avoidance, you might get this really weird, janky behavior where I want to kind of bounce back and forth. And we kind of saw that in lab, actually. Okay. To get believable behavior, we'd like the wall avoidance behavior to consider what pursue is trying to achieve. So almost like, hey, wall avoidance, I'm trying to chase the character. Don't just push me off in a random direction or away from the wall, but rather push me, keep me going in the same direction. That is the idea that we want you to do with assignment 1. Keep me going in the same direction, right, as where I'm supposed to go to pursue the target, but at the same time avoid, kind of moving around the wall. Because again, in this situation, avoidance means move this way, like the exact opposite, almost like using flee from the wall. That is some ways that we can do. We can use flee as we move towards the wall, and pursue when we're moving towards a character, which is kind of conflicting. Here, we're not using flee, but rather we have a secondary or sub-goal that we want to move towards to avoid the wall while maintaining the orientation we want for our autonomous to chase our target. Okay. Obviously, taking all this in mind, what it does is it increases the complexity of the steering algorithm. That's what it does, because just like we saw in lab, we try and create an effect, and what it's doing is when we combine something like look where you're going, which is a steering algorithm, with seek, it becomes more difficult to do. It looks nice, but it can be really challenging. So what the author here has introduced, which I really like, is something called the steering pipeline. And really what we're doing is we're not just simply blending or prioritize, but we're using something like cooperative arbitration as well. Okay, trying to say, hey, what do we really want to go to? What is our real goal here? What is the goal of our movement? Is the goal of our movement to get closer? That is what takes priority. Yes, we want to avoid walls, but our main priority is to move closer. So can we not avoid a wall and move in the right direction? That's what it wants to do. And we can use some blending and some priorities along with pathfinding and line of sight to improve the algorithm and have a better result. That's the idea behind it. Okay, so again, we have the steering pipeline might look like this, where we have a targeter, and we have a decomposer, which decomposes all of the um, steering behaviors in a series, as an example. And we have several constraints that it keeps track of, right? As an example, we know that there's a wall. We know that we might need to keep a certain distance depending on what type of loadout the autonomous character has. Example might be if my autonomous character has a ranged behavior, which it wants to stay back, further back, some kind of separation criteria from the thing that is chasing, because I want to be able to fire weapons. If I'm too close, I can't fire the weapon, right? That kind of thing. I take the constraints in mind and I put all those together, and then I get an output acceleration, whatever that acceleration is. Remember, the acceleration is going to be a vector that has both magnitude and direction, right? Which is going to basically use like a carrot and stick idea to move our character in the right direction. Okay. So again, the 4 stages of the pipeline are: targeters work out where the movement goal is. Where do I want to go, right? Decomposers provide sub-goals, and this is the idea. The decomposer says, hey, you know what? I want to avoid this object, but at the same time I want to get to the goal. Let's set up a sub-goal as an example. And then constraints limit the way an autonomous character can achieve a goal. Example, the constraint would be, hey, avoid the obstacle. That is the constraint, okay? And the actuator limits the physical movement capabilities of an autonomous character, so it slows things down, speeds things up, moves things laterally, or whatever, reorients the character's facing, and so on. Okay. And we can also look at it more complex like this, where we have, here's our direct route to the original goal, and we have a sub goal. We can use this idea of a radius, the original radius, right, of where we're going to move. But this is we don't really want to get too close. So we have a sub goal away from this kind of like area of danger for the where the direct route would be able to basically hit the obstacle. We don't want that. We have a sub goal and we move toward that sub goal. Okay. There's also another scenario where the sub goal or the original goal is right through the character. That's the example of the obstacle that I gave you earlier, where I'm moving right through. All right. So that is the other option. And then you might promote 2 different sub goals, sub goal A or sub goal B. Same idea, which is what I talked about earlier. So this idea of using some kind of steering pipeline or using some kind of arbitration is the recommended approach, in addition to using line of sight or raycasting behavior. Okay. Is raycasting okay? Can it work? It can, but it can look really, really janky, like we thought before, right? But introducing a sub goal, what either one or an optional sub goal above, depending on which random direction you're going to turn the character, right? The autonomous agent is probably the right way to go to mitigate multiple priorities, for the agent, which is what we're giving you in assignment 1. Okay. Questions around combining steering behaviors, the challenges of doing so, how do we do flocking, and all that kind of stuff. Simon says, is the sub goal the circle or the points in the circle? The sub goal is just outside of the circle here. So you see the sub goal here, here, right? So here's the sub goal over here. And the circle would be, an area, the radius that if you went to that someplace on the circle, right, at least from one side or the other side, you chances are would avoid hitting the target. That's the idea behind it. If the sub goal is too close, that's not a great sub goal. It's got to be kind of positioned so that it's outside of the radius where I'm going to hit the actual object by accident. I want to still avoid collisions, right? And still get to our target. Now, there's a couple ways they're showing here, and they're saying let's calculate the margin of error, if you will, where we want to kind of be within this band in order for me to avoid collisions, right? And that's why the sub goal is put at least some distance away from the danger zone. Okay, that's the idea behind it. So if this is the danger zone, then we want to put the sub goal away from the danger zone as much as possible. But within reason, because if it's too far, then it's going to actually take too long to get to the goal. Sam says, sir, is it okay if I created a Discord for the class and can I put the invite into the chat? You can go ahead. Yeah. There's already a Discord for the class, but again, that's something that's been out there for a long time. You can use the same one that you had before. There's two Discords out there already that people are using. So you can continue using that one, or if you want to make a new one, go ahead. Any questions around this? So this week, what we're going to be doing is in Lab 3, and you're going to have much more succinct directions in Lab 3 that Alex is going to give you first, and then I'm going to kind of use the same ones, are add the obstacle game object to the scene. That's what you're going to do. You're going to include additional controls in IMGUI for the obstacle and for the whole obstacle avoidance scenario. Because now we're handling two scenarios, right? The seek scenario and the obstacle avoidance scenario. And so we want you to be able to handle both. And then what we want you to also do is consider methods to improve obstacle avoidance. And there might be some algorithm enhancements that we might be talking about in lab, like a sub-goal, like doing those kind of things. How do I do that? And so we'll start off with a very basic obstacle avoidance. We'll implement some primitive ray casting to get you guys to understand how that's done. And the way it works is through line-line collision detection, and then further than that, a line AABB collision detection algorithm that where the ray can detect that you don't have line of sight. So again, if your line of sight is interrupted, right, then you need to avoid, right? You need to avoid the obstacle. That's really what you want to try and do, right? So if I draw, like I said, a line of sight, going back to this, I draw a line of sight, and the line of sight is just like a line from the agent to the target directly. If I draw this line of sight and there's something that hits in the middle, then I know there's an obstacle. And sometimes this can eliminate things like short-sightedness, right? Short-sightedness. And this is the thing that you want to try to avoid, right? So, and we can still use line of sight with a couple of rays as an example on the side where they're pointed this way, like whiskers, or they're pointed kind of to the sides. Either way, what it can do is it can help us try and figure out what the sub goal is going to be, right? If there is any, and you don't have to use a sub goal. This is just an option, right? So let's put that in there as the sub goal is optional, right? Because we can figure out a lot of way around an object, right? Just by using line of sight as an example and additional rays, right? The other way to do it, and this is, again, this is a hint for you guys, is, here's a hint, slow down your agents when detecting an obstacle ahead. Okay, so cut the speed down, maybe cut it in half or a quarter or whatever. So that's kind of the hint, because if you don't do that, then what's going to end up happening is as soon as you, if you keep accelerating maximum speed until you get to a certain point, it'll be too late. Your turn rate might prevent you from skirting the object. You'll probably hit the object anyway, right? Even when you start turning, like I showed you, right? So slow down, slow down, slow down to the point where, and obviously when I say slow down, that means decelerate. It does not instantly cut, right? Decelerate. I think I spelled that wrong. But that's the idea. Did I spell it wrong? Now I'm going to look it up because I'm just, no, I spelled it right. Oh, look at that. So decelerate when I say slow down, decelerate your agent when detecting an obstacle ahead and then start turning, right? That's what you want to do. Okay. Any other questions around combining steering behaviors or anything like that? One thing I wanted to do before we leave for the day is I wanted to talk about some possible solutions for Lab 2, right? So I know we talked about Lab 2 in some detail, right? And I think I have section 400, which is what I did at the end of the day for Lab 2. This is where I made the video for Lab 2, I think. Let's make sure that this is the right one as my object looks. And one thing we talked about was what about rotating an object, right? And what I'm going to include with you guys in the util library for you guys is something called rotate point. And what rotate point will do is you can rotate a point. I talked about this in lab. around a pivot. So why would I need to do that? Well, like we talked about, if I go back to my agent, as an example, if I rotate an agent and I have an AABB type collider that's set up for the agent. So let's suppose I have a AABB type collider for this guy, right? And the AABB type collider goes around the agent like this, right? Well, when I rotate the agent, it's not going to do this, right? It's not going to do this with the collider. It's actually, the collider is going to stay where it is, right? And that collider is actually going to create a visual, it's going to be a conflict between what we see visually and what we see and how it collides logically, right? So the right thing to do is when we're actually rotating an agent like this, right, is when the agent gets rotated, what you're supposed to do is also rotate its collider. So example, if I rotate the agent this much, then the new collider will be set up like we talked about, which is still going to adhere to AABB like this. This will be the new collider. The collider will change shape to accommodate the rotation of the agent, so we can still do AABB type collision detection. If you don't change the shape of your collider when you're rotating, then you run the risk of having an issue. And if you think about trying to rotate your colliders, and that's the way you want to do collision detection, that's a different way of doing collision detection. That is, object aligned bounding box, or OABB, which is way more computationally expensive, right? And an overall more complex algorithm. So if you want to avoid complexities, my friends, then you want to consider how this is going to work, right? You want to avoid this situation. And some people have tried to make their own OABB type calculations in the past. That's fine if you can pull it off, but generally this is not recommended. It's more recommended that when you rotate your agent, then the original collider boundary, which is this one, will change shape to the rotation, what your agent is rotated to create a good, solid collision detection. Now, why am I bringing this up? Because it may be the case that when you're rotated and you're kind of coming into the target, your AABB is not going to look like this. It's rather, if I take this object, let's just move that object by itself, right, over here to the target, right? If I take this object by itself, let's just copy paste it for a second. Who cares about the lines? So copy paste. And I move this object over here. Let's just rejig the rotation. So it's this way. Chances are, if you're going to go to the target here, from here, you're going to go this way. Chances are your AABB is still going to be this way, right? So where you have a AABB that is in this kind of shape. So it'll be like something weird, and it'll be towards the center of the target. So it might be something like this. That's what it will look like from here, because it's kind of the same shape as this one. It's not going to change orientation unless you make it do so, right? So this is the problem that you might have. Okay. The other opportunity that I talked about during lab is, what if you didn't do this at all, but rather you used a circle type AABB type collision. So circle, right? So it doesn't matter whether you're oriented. If you change orientation, the circle is still going to hit. And because the circle is going to be, kind of in the front of your object, let's say, that's going to still bound. It's going to be a bounding volume that is in the front of your object. It doesn't matter what the orientation is. The challenge with this approach that we talked about in lab is, what if you have another object that's colliding with your spaceship in your game, which is here, like in this area? So it's going to be a AABB and kind of circle type collision detection. There is no visual collision, but there'll be a logical collision, which the player will instantly detect and remove them from presence. It will kind of reduce their presence and immersion in the game. So this is something that might cause more of a problem. Easy to figure out in our example, but bad potentially in a real world scenario. Okay, anyone have any questions around this idea? You're going to have to do something when you do this kind of thing. When you're changing your agent's facing so it looks in the right direction, and you have that old bounding box, right? You can get into into the problem where it just won't look right. It'll make the noise, it'll have the collision. And so how do you work it out? You can work it out with a formula like this, where you have a rotate point, and what you do is you rotate each of the extents, the top left, top right, and bottom left of the collider. So again, if I was going to draw it here as an example, right, just to show you, you would run this rotate point on each of the points in your collider, right? So you do something like, as an example, you'd have the top left, let's say top left, right here. You rotate that point, and you'd rotate the top right, right? These are the 4 points you care about, right? This is the bottom right, and this is the bottom left. You want to take those 4 points, right? And you want to rotate them around a center. So this is like, let's say the center here, center C, right? Let's move that here in the middle approximately. And when you do that, you want to rotate around this pivot. That's the pivot point, the center. You want to rotate these points. You give it an angle, and you can run this same rotation algorithm around these 4 points, 1 point at a time, until now you have a new rectangle that you can create, a new bounding area with those 4 points. That is the right way to do it. Okay. So questions: will there be marks lost if your collider doesn't look right? Well, you might get slightly less marks if, for example, your bounding area, when you do your collision detection, it shows it. You hear the collision happen, but you don't see it happen. As an example, because your bounding area is wrong. Okay, so just FYI. So there's different solutions here, and this is one of them. It's more complex. It still might create a visual problem, but not as bad as not rotating it at all. Questions around this problem, and I'm going to give this same algorithm. I'm going to give this same algorithm to Alex, so he can include it in his labs as well. Yes, Simon, absolutely. You can use whatever collision method you want, whatever collision shape you want, or bounding area, as long as it looks right. Absolutely. Okay. All right, so that's really it for today. I don't want to go too much further than that. I'm going to take questions now. I'm going to stop recording on YouTube and take some questions related to the assignments or anything else that we've done. Okay, so let's just stop recording now, and we'll go from there. All right, so we're not recording on YouTube anymore.